Hello, my name is Jackson Herndon, and today I'm going to be talking about dislocations and plastic deformation in metallic structures. So to get us started, we'll talk about plastic deformation, which occurs as dislocations move along slip planes. Plastic deformation is permanent, meaning that once it occurs, the material will not naturally bounce back or revert to its original shape. Common occurrences of plastic deformation would include crushing a soda can, bending a paperclip, or really any instance in which forces act on a metallic structure to the extent of changing that structure's shape. Next are dislocations, which form as a result of the solidification of a material as well as the stress applied to a material. Dislocations in a material can be controlled, and they form as a result of applied stress. Typically, for a dislocation to occur, there must be two applied stresses in opposite directions, which act parallel to the slip plane. There are two main types of dislocations. First, an edge dislocation occurs when an extra half plane of atoms moves through the crystal lattice and reappears on the other side. This occurs when a shear stress acts parallel to a slip plane and in a plane where slip is occurring. One model which does a great job of explaining dislocation motion is the ripple in the rug model, which vertically concatenates two planes and demonstrates that when an edge dislocation occurs, the half plane of atoms, which is seemingly shifted from the front side of the plane, actually causes a chain reaction within the top rug when a force acts on it. The general idea behind this is that when an atom moves through the crystal lattice through shear force, a reaction is set off which moves all of the other atoms through their crystal lattices in equally sized increments until eventually all atoms in the top half of the structure have been translated by the same distance and in the same direction. This is why materials deform through dislocation motion when stress is applied. Now, in order to stop dislocation motion from occurring, more dislocations would actually need to take place. As certain dislocations occur, they could simultaneously collide with another dislocation which would entangle the two. Once entangled, the two dislocations are actually stronger than before and would require a greater shear force to dislocate them again. This is why cold working, or the process of strengthening a metallic structure through induced mechanical stress, is such an effective method. The second type of dislocation is a screw dislocation, which occurs again as a result of two opposing forces, aka shear force. However, in this case, the shear force initially causes the upper section of the dislocation to twist in the direction of the shear force. As force is continuously applied to the structure, the bonds on the front of the half plane would shift through the crystal lattice while the bonds on the back would temporarily remain in their original position. However, as stress persists, a dislocation would glide across the lattice, causing the entire half plane to shift, essentially creating the same result as an edge dislocation. It is important to note that metals tend to deform along the closest packed directions and the closest packed slip planes. This is because when atoms are more closely packed, their bonds are stronger, making it easier for them to reform after being broken. Now, there are two important types of slip systems. The first is a body-centered cubic slip system, which occurs in BCC crystal structures. In BCC structures, deformations occur along close packed directions, but they do not have a close packed plane. It's important to note that these close packed directions lie along the body diagonals and are of the 1-1-1 group. Likewise, the slip planes for this structure are 1-1-0, 1-1-2, and 1-2-3. On the other hand, we have face-centered cubic slip systems, which occur in FCC crystal structures. In FCC structures, deformation occurs along close packed directions, which lie along the face diagonals. The FCC crystal is more closely packed than the BCC crystal, and unlike the BCC crystal, the FCC crystal has a close packed plane. These are my sources, and thank you for listening to my video.